today is the last lecture for this course, and as we have decided in the last lecture, today we will try to find geodesics on a surface, which is a very special kind of surface. I mean, it is again surface of revolution, but okay, let me write the equation first. But we want the Gaussian curvature to be constant -1. In the last lecture we have seen Gaussian curvature 0, what are the surface possible surfaces? We have seen Gaussian curvature constant +1, that only part of the sphere, and today we will see if such a surface exists or not and what happens to their geodesics. It is very interesting. Phenomena starts happening here, that our regular sense of geodesics that fails in this kind of surfaces. These are typically called hyperbolic surfaces, because Gaussian curvature is -1. So, that is, you remember, k product of the two principal curvatures, and such Gaussian curvature constant -1, that all the points are hyperbolic. So, such surfaces are called hyperbolic surfaces. So, in such surfaces all points are hyperbolic. Now, we know that for surface of rotation the Gaussian curvature is given by f double dot by f dot, and we consider unit speed curve. So, this is for our gamma u was f u 0 g u unit speed, and that means that f dot square plus g dot square equal to 1. Dot f dot is with respect to df du, right. Well, now this, if this is equal to -1, this gives rise to a differential equation. Correct. This is a linear differential equation whose general solution is f u equal to a u plus b e power e u. Okay, I can take any curve for that matter. So, take a equal to 1, b equal to 0. So, f u equal to e u, and what will be g u then? From this equation g u will be integral 1 minus e to the power 2 u du. Now, you see, to integral to make sense, we must have u less than equal to 0. So, we must have, so I draw the picture a little bit. So, instead of taking this is z, this is x. So, my curve must lie, okay, I am not drawing the curve right now, curve must lie in this region, because x has to be, u has to be negative. So, I will draw the curve, but let us see if we can do little bit more about the before we can actually draw the curve. Let us try to evaluate this integral. This integral if you evaluate, this comes out to be root over 1 minus v square plus okay. Then if you put W equal to V inverse, then this will come out to be one minus e power 2 u minus cos hyperbolic e power u. So, there will be some constant, but I omit the constants because we need only one curve. So, what I get? My f u is e power u and g u is this. This is g u and f u is e power u. So, the profile curve, in the profile curve, if I put x equal to f u, then z and z equal to g u, then z is actually root over 1 minus x square minus cos hyperbolic inverse 1 upon x. So, this curve looks like passes through 1 0 in x z plane. This curve looks like, so this is the point 1 0 and such a curve has a name, is called trictics. Now, we will rotate it around z axis, y axis is here. I am not drawing the y axis here, because drawing becomes difficult in that case. So, it is called tractis. This curve is very, so while we rotate around z axis, we get a figure like this, and this surface, this is known as pseudosphere. Why pseudosphere? Maybe I will take when you this, okay, let us see why it is called pseudosphere, maybe I will explain. But this curve tractis has a very interesting property. What happens that if you take any point on the tractis, let us say P, and you draw the tangent through P and let it hit the z axis at a point Q, then the length of PQ, this is always constant. What does it mean? Wherever you take your P and you draw the tangent line, let it cut the z axis at Q, some point Q, the length of PQ is always a constant. It does not depend on the parameterization of the curve. So, I put it this as an exercise, nice exercise to solve. The surface generated is pseudosphere. So, let us try to find out geodesics on pseudosphere. Okay, first I know all meridians are geodesics. All meridians will be geodesics. Any surface of rotation we have proved in general that all meridians are geodesics. That what are the meridians? These are the parallel lines of the profile curves. Now, to find, and parallels are never geodesics here, because to be parallel geodesics I must have f u constant, but here f u is e power u, never constant. So, parallels are never geodesics. So, that is a remark I make here. Parallels are never geodesics here. Okay. To find the other geodesics, so you will be using Clairaut's theorem. Okay. I know the first fundamental form of this surface is how much? This is always given by du square plus fu square dv square. So, in this case this is du square plus e power 2 eu dv square. I reparameterize this curve by putting w equal to e power minus u again. Then the surface looks like sigma w v equal to 1 by w, you check it, I mean this is very easy, cos v 1 by v sin v 1 minus 1 by w square cos hyperbolic inverse w, right. So, let us take gamma t be a GT, unit speed geodesic, on the surface on the pseudosphere. So, let us take gamma t to be sigma tilde omega t v t. Unit speed will give us v dot square plus w dot square equal to w square. How do I get it? Because if I see, if I reparameterize, after reparameterize, the first fundamental form becomes dv square plus dw square, this thing, and the speed of the, and if I take and integrate the first fundamental form, I get the length of the curve, and unit speed, I am taking unit speed curve. So, this will give us that v dot square plus w dot square w square. So, let us put a mark on this equation star. Now, what I know? I apply Clairaut's theorem now. What is constant? Distance from, so distance, so fu, now it is fw, not fw, I mean recall what happens Clairaut's theorem. If fu sin psi, or sin is, psi is the angle between gamma dot and the meridian, gamma dot and t, then this remains constant. So, by Clairaut's theorem what we will have, that one, now distance is 1 by w, because I have put w to be, fu is e power u, and I have put w equal to e power u, e power minus u. So, it is distance is 1 by w sin psi equal to 1 by w angular momentum v square, that must be constant. So, I get v dot equal to w square c. Now, so c is the constant. Now, if I put c equal to 0, then v dot equal to 0. So, v is constant again. So, that is the meridians, we get back the meridians. Okay. Now, c not equal to 0, then by star, what was star? This fellow, I get w dot equal to plus minus w 1 minus c square w square. Hence, along any geodesics, I must have v dot w dot, but then I can write it, I can remove t part dv dw, that is equal to plus minus c into w 1 minus c w square. If you solve it, you get v minus v naught is equal to plus minus plus 1 by c 1 minus c square w square, that is v minus v naught square plus w square equal to 1 by c square. So, this looks like circle in coordinate in xy I mean vw coordinate, but if I look at on the surface, so geodesics will be, geodesics are image of, but image under sigma tilde of parts of circle, because this is a circle in wv coordinates, parts of circle in wv plane and lying in the region w greater than 1. Why? Because u is less than 0, w is e power minus u. Remember each time this was the reparameterization, u is less than equal to 0. So, w is actually less than 0 you can take, then w is greater than 1. Okay. All these circles, so all these circles has center on v axis, v naught 0 is the center for different v naught, and intersects v axis perpendicularly. So, if I draw this mid in wv plane, this is w equal to 1, this is w axis, v axis. The geodesics looks like this part is not there, part of this semicircle. Okay. And what happens to the meridians? This you check, meridians are mapped to straight lines parallel to w axis. So, these straight lines, they are also, they are meridians and they are also geodesics. These are the only two geodesics available for pseudosphere. This picture of pseudosphere is called the upper half plane model. So, this is called UHP model of pseudosphere. Actually, it is connected to so called, this is the beginning of, as I said, hyperbolic geometry. So, there is some notion of projective planes, and if you look at the projective planes, then geodesic on projective planes. So, pseudosphere in the upper half plane is the specifically the projective planes, 2 dimensional projective plane, and pseudosphere on geodesics are straight lines and semicircles. So, if you want to continue with this geometry, topic of geometry, or you would start any course on differential geometry from here, you will be talking about the language of manifolds and also the language of, I mean this whatever we have, as I said I in the beginning, we have not actually uttered the word manifold throughout this course, but the differential geometry course will start with the word manifolds, but you will have the confidence to go ahead, because the manifolds what you see the 2 and 3 dimensional manifolds what you will be working on, they are the curves and surfaces what we have dealt with. Okay. So, that is the beginning of differential geometry course and end of curves and surface course. But we are left with one thing that I promised sometime that I will do, and so for the last part of the lecture, last part of this lecture series, I want to do this part of, I want to I want to just complete that gap, and that is about quadratic surfaces. You recall, while talking about principal curvatures and its geometry, we have observed that by applying rigid motion possibly, rigid motion in R3 and reparameterization, if I have a P on a smooth surface, then near P the surface looks like something around z equal to half k1 x square plus k2 y square. So, it looks like a quadratic surface. So, for k1 and k2 are principal curvatures. See, here we make a definition and then we make some observation. S in R3 surface, smooth surface, smooth regular surface, okay. We will see the smoothness and regularity condition. Surface is called quadratic if it is, okay, let us say it is of the form what does it mean? So, R is a vector x y z, A is a 3 cross 3 symmetric matrix, B is a constant vector, B1, B2, B3, and C is some constant. So, if you write A to B, I write in this way A1, A2, A3, then A4 here, A4 here, A5 here, A5 here, A6 here, A6 here. If I write it in this way, then S becomes similar just Ax square, A2 y square, A3 z square, 2A4 xy plus 2A5 yz plus 2A6 zx plus B1x plus B2y plus B3z plus C equal to 0. This is a quadratic equation. So, if you do this fellow with this matrix, you get this one. See, this is not necessarily always a surface. Why? For example, if you take A1 equal to 1, A2 equal to 1, A3 equal to 1, other constant 0, then you get x square plus y square plus z square equal to 0. This is not a surface, this is just a origin. Similarly, if you take just A1 equal to A2 equal to 1, other constant 0, you will get x square plus y square equal to 0. This is not a surface in R3, right. This is just pair of straight line. Similarly, if you take this say A4, only A4 equal to 1, A4 equal to half and other constant 0, then you will get x y equal to 0. So, this is again not a circle, it is a union of two intersecting straight lines. So, this any quadric may not be a surface always. So, I need condition on A1, A2, A3, A1, A2 the AIs and BIs, but what is true is this proposition, and that I want to write down the entire this proposition, will not prove it, and proof is but I will indicate what how I will tell you how to prove it. The proof is very easy, but it is very it is the total classification of all quadric surface, all quadric. It says by applying a rigid motion in R3, every quadric in which all the coefficients are not all 0, okay, all the coefficients should not be 0, can be transformed into a surface with Cartesian equation one of the following. 1, ellipsoid, this is of the form P Q R throughout are non-zero constant, okay. Either ellipsoid or hyperboloid of one sheet, this is x square p square plus y square q square minus z square r square equal to 1. Hyperboloid of two sheets, that is x, that is let us write it this way, z square r square minus x square p square minus y square q square equal to 1, or elliptic paraboloid this is simply x square by p square y square by q square equal to z. Hyperbolic paraboloid This is simply x square minus p square y square p square equal to z. Okay. 6 a quadric cone which is simply x square p square plus y square by q square minus z square by r square equal to 0. Elliptic cylinder which is simply hyperbolic cylinder parabolic cylinder maybe just a plane x equal to 0 or y equal to 0 or z equal to 0, I mean up to rigid motion, two parallel planes two intersecting planes straight line. In this case this is no longer a surface, and finally single point. These are all 14, only 14 exclusive possibility for a quadric surface up to rigid motion. Now, how do you prove it? Proof is that I have taken this A, a symmetric matrix, right. So, that means this A was a symmetric matrix. Three cos 6 symmetric matrix. What do we know about symmetric matrix? That if A is a symmetric matrix, 3 cos 6 symmetric matrix, then by applying I can find a orthogonal matrix P, so the P transpose P is diagonal. So, that is and applying orthogonal matrix to coordinate system means it is a rigid motion, it is a rotation. Maybe you have to follow by translation, okay, you don't, and okay, first you go to the rotation, so you get a D, diagonal matrix. Now, if I have a diagonal matrix, then if you look at these equations, this will become, no, that is not this one, this one, this will becomes easier to handle. Now, by translation, depending on the entries of the diagonal and B1, B2, B3 and C, you will get one of this equation 1 to 14. So, the proof is very easy, you can try it yourself, and for instance, okay, one may continue with many examples. I will write down one example in the assignment 4. So, that is the end of this course. Thank you. I hope you get some benefit out of it. Thank you.